Beneath the surface lies a hidden network. Fungi communicate through bioelectric signals, forming living systems that sense their environment and respond to change. These signals reveal patterns of communication that were once invisible. This summer, we joined the Underground Brain Project to explore this underground intelligence.
We would like to acknowledge that this video is being made on the lands of the Turrbal and Yagara peoples. And one of the amazing things we have in the lab is this beautiful artwork of a desert truffle dreaming, the Dintapanta Jacopa, which is from Central Australia. So the Underground Brain Project actually started as art meets science. So an artist, Bianca Tainch, approached me to hook up, would you believe it, a robot to the bioelectricity in the mycelium. That's the underground part of fungi. And we started trying to work out what are we sensing in the fungi. So everybody is aware that brains have electrical activity, but not many people are aware that every cell in biology has electricity, and in particular that there is bioelectrics in things like fungi. So the project has an amazing ability to speak to the public in a really interesting way. So there's a public understanding of science component of what's going on. We want people to understand fungi better.
Hey, I'm Archie. I'm studying electrical engineering. This summer, I was tasked with designing a probe that allows us to inject waveforms and record voltages from the mushroom packs. This was my final design. It's got a voltage-controlled current source and differential voltage sense, so we can get some precision recordings. Here's a live voltage reading right now from this mushroom pack. Hopefully in the future, this will allow us to start to decode the language of the mushrooms, and maybe one day we'll be able to talk and communicate with the fungal networks.
Hi, I'm Connor. I'm studying electrical and computer engineering. My job for this project was to develop an algorithm for figuring out how the mushrooms are growing over time. And I do that through optical flow analysis. As you can see here, it shows the vector field of mushroom growth. And I also developed viewing software that allows you to see the mushrooms in real time. And this collects data that will be fed into this algorithm so we can figure out how well the mushrooms are growing.
My name is Mitch. I study mechatronic engineering, and my task for this research project was to analyze the data that we collect of the electrical signals to find some interesting patterns. And one of the techniques we chose was Gramian angular analysis. So that consists of converting our signal into a sort of polar form, which can then be used to calculate the Gramian angular field matrix to hopefully pick up more interesting patterns with a convolutional neural net.
Right, so the kit here that we have here for measuring the electrical signals consists of what we call an analog to digital converter here. So device here will measure the electrical signals, so measure things like voltage. And we have what's known as the M5 core here. So this one here will actually measure the output from the analog to digital converter there, and it'll store it onto an SD card that can be used to access the data later. So I think the big questions of this project is to find out more about the environment of where things are. So for agriculture, that's trying to find if crops can grow better. Fungi, I think, is sort of the next level of sensing. So it will sense the environment, and it could do all sorts of things. Perhaps it could sense toxins in the environment and so on like that. I think there's some really interesting questions that you can ask.
Hello, I'm Shafa, and currently I'm studying computer science in data science. Here I supported to branding our project as MycoWave, and I created a public project on iNaturalist to share the bioelectrical recording signals to the public. By using the portable kit, I recorded the signals and visualized the data through plots, and then I uploaded interesting observations so that the researchers and the broader community can explore the fungi bioelectrical activity. And also, I work with Gabe, a PhD student in analytical chemistry, to share knowledge about iNaturalist through fungi spotting and documentation. Through MycoWave, I hope to make these hidden bioelectrical signals more accessible and encourage engagement to the fungi research community and also students.
So terahertz is a wavelength which sits in between infrared and microwave wavelengths in the electromagnetic spectrum. One of the interesting things about terahertz is because it's such a low frequency, a low energy photon, it can measure the conductivity of materials, which would be the equivalent to what happens at low frequency FTC. So we can use terahertz imaging to image the change in conductivity in the mushrooms, which is a marker of its electrical activity without actually being in contact with the object. We know from putting the probes in, it takes a while for the probes to interface nicely with the mycelium, and presumably that's because it's repairing itself around the probe and it takes time for that to happen. Whereas if we can do it in a non-contact way, we're not disrupting that and potentially affecting what we're measuring. Well, hopefully we can do our signal recovery without actually having to be in contact with the mushroom, and potentially, as the technology evolves, getting some sort of handheld scanner which will be able to be deployed in the field and be able to image these things in the wild.
Through this project, we explored one of nature's most fascinating hidden systems. By combining engineering, data analysis, and public engagement, we contributed to understanding the underground brain.